Thite. I'm part of a team from the Georgia Institute of Technology, and today I'll be discussing concurrent neural tree and data preprocessing AutoML for image classification. So deep learning methods have been shown to improve state-of-the-art performance in a variety of tasks, including natural language processing, computer vision, and speech processing. As a result, there have been many different task-specific model architectures and hyperparameters that have been invented, including transformers and convolutional neural networks. However, the problem is that it is often necessary to spend copious amounts of time tracking and experimenting for optimal performance. A potential solution to this is neural architecture search and hyperparameter search. These solutions treat finding the task-specific optimal architecture and hyperparameters as a search problem. So there are three components for neural architecture search. There's a search space, a search strategy, and a candidate network performance estimation strategy, also known as a selection function. We will be focusing on evolution-based methods, including NEAT, HyperNEAT, CoDeepNEAT, and EMADE. So let's focus on NEAT first. NEAT stands for Neural Evolution of Augmenting Topologies, and it is one of the first genetic algorithms for neural network topology evolution. NEAT directly encodes neurons, their weights, and neuron connections as genomes. It then creates a population of these genomes, which then undergoes a biologically inspired evolutionary process, during which genes can either mutate, where their weights and connection values will randomly change, or mate, where portions of two genomes will combine to make a new child genome. However, the issue with this is that direct encoding of neurons to genes is not feasible at larger scales, due to the amount of memory required to store millions of neurons and the time it will take to evolve larger and deeper neurons, one neuron at a time. So one solution to this is HyperNEAT. HyperNEAT encodes neural networks indirectly by specifying layer parameters and sizes rather than individual neurons. This allows NEAT to be scaled up and to be used to evolve larger and deeper neural networks. The next evolution of NEAT is in CoDeepNEAT. CoDeepNEAT allows for multi-objective optimization and returns a list of codominant networks. This allows CoDeepNEAT to optimize for metrics such as accuracy and size simultaneously, and it also allows CoDeepNEAT to perform coevolution. Coevolution is evolution of submodules and modules, or genes and the sequence of genes in the genomes, concurrently. This allows for greater evolution efficiency. CoDeepNEAT is used in the Leaf AutoML system. It creates networks from scratch, trains them for 8 epochs during the CoDeepNEAT evolution process. Once the best network is selected, it is then retrained from scratch for 300 epochs. Leaf achieves around 7.3% error rate on the CFR10 dataset. However, one major drawback of current neural architecture search solutions is that there is a lack of involvement of data preprocessing in the search space. And this is particularly important since data preprocessing can dramatically affect the quality of the resulting model. So we should allow the evolutionary process to act upon these functions as well. For our solution, we'll be using EMADE, or the Evolutionary Multi-Objective Algorithm Design Engine. EMADE is a pre-existing automated ML framework based on the DEEP framework, and it includes data processing functions in its primitive set. This allows EMADE to evolve traditional machine learners and data preprocessing algorithms concurrently using vector-based genetic programming. EMADE expresses its algorithms as trees, with functions expressed as nodes and parameters expressed as terminals. Nodes are computed in order of decreasing depth, with outputs from child nodes being passed as inputs into their parent nodes. EMADE's evolutionary process follows a similar algorithm to NEAT and other genetic algorithms. First, an initial population of trees are created and evaluated, and then during each generation, a certain number of trees are selected, and EMADE uses the NSGA2 selection function, and these trees are used to create new trees to add to the population. And these new trees are created via mating and mutation functions in a similar way to NEAT. While EMADE has been used for a variety of domains, it has never been used on deep learning applications. Therefore, our contribution is to extend EMADE to optimize neural network architecture and hyperparameters. We will be doing this by including neural network relevant primitives and terminals, thus adding neural networks to the search space, as well as adding neural network centered mating and mutation functions, which will aid the evolutionary process for neural networks. Our goal is to show that modifying EMADE to evolve using both data preprocessing functions and neural network primitives improves accuracy on CIFAR10 and can potentially improve on state-of-the-art algorithms. So our first function we added was an NN learner. The NN learner takes in 4 arguments, data, represented by arg0, a layer tree represented by the mobile net input layer and the output layer, the batch size represented by the number 9, and an optimizer, in this case Atom. It takes in these parameters, and it creates a neural network using the Keras functional API. It trains this network on the trained subset of the data, and validates it based on the validation set. But how does the NN learner know what exact architecture to make? That's where the layer tree comes in. The layer tree is a pre-ordered list representation of the neural network tree, and it is passed into the neural network function as that second parameter. We built a set of layer primitive functions, and these primitive functions add Keras layers to this tree, resulting in a tree-structured computational graph when we chain several layer primitives together. So for example, in this tree on the bottom left, we have the mobile net input layer primitive function. This function creates a layer tree and adds in a keras.applications.mobilenet function or a mobile net neural network to it. It then sends this layer tree to the next function, which is an output layer, which adds a dense layer with the sigmoid activation function to it, and sends it to the NNLearner primitive. The NNLearner primitive now knows what exact architecture to create. However, only using a list only allows us to create sequential models. If we add in concatenate layers, which can concatenate the output of multiple layer trees, we can increase the complexity of the network and enable tree-structured neural networks, as you can see on the right. We also added in pre-trained layer primitives. We did this because we saw that pre-training on ImageNet is shown to yield significant performance gains. We add in each pre-trained network as a single layer, as you could see by the previous example with the mobile net input layer. EMADE is easily able to add other primitives before or after this layer. In particular, we implemented VGG, MobileNet, and InceptionNet architectures, with using the pre-trained ImageNet weights for all three of them. However, we left these pre-trained weights to be unfrozen, which allows EMADE to update these weights during the training process. We also allowed EMADE to optimize various network level and layer level parameters. As you can see, for almost every single layer, EMADE can optimize the output dimension and the activation function. And for certain layers, it can optimize, for example, for dropout, it can optimize the dropout percentage. There's also various network layer parameters such as batch size and optimizer. EMADE supports over 150 primitives that operate on image data with more than 60 signal processing functions. We included these functions as part of our own primitive set because we felt that they would be helpful for some image classification tasks, such as we include primitives such as the hair-like features, edge detection filters, grayscale conversions, and many more. We also added in mutation functions to aid neural network evolution. Specifically, we added the ability to randomly add a layer, randomly swap a layer with another layer, randomly remove a layer, randomly change the activation function of a layer, and randomly change the optimizer used. In the same vein, we also added in mating functions. These mating functions improves mating between tree-based neural networks, and it does this by type checking for layers to prevent degenerate individuals. We do this because if we'd have a subtree that has a component as a normal data preprocessing primitive in it, and we switched out with a subtree that is purely layer tree, the layer tree will be modified. The layer tree will be degenerate because there will be a mismatch in the layers sizes. By type checking, we can help prevent degenerate individuals and can evolve more efficiently. So we added in a single point crossover function, and we also added in a modified version to aid in expanding neural network size. In this modified function, instead of each subtree getting swapped, each subtree is appended to with the subtree from the other parent in order to increase layer depth and increase overall complexity of the network. For our experimental setup, we decided to test our implementation on the CIFAR10 dataset. The CIFAR10 dataset is a 60,000 32 by 32 color images in 10 classes, with 6,000 images per class. And classes consist of different vehicles and animal types. There's a 50,000 image train split and a 10,000 image test split. We seeded 16 hand-created NN learners in order to bias the evolution process to creating neural networks. Each one follows the same general algorithm of being a pre-trained network followed by an output layer. And the pre-trained networks are either VGG, MobileNet, or Inception. And Atom is set to be the optimizer. The batch sizes varied between these 16 networks to be some number between 1 and 9. The remaining individuals in the population are all randomly generated. We performed two runs with the same seeded individuals, but with different run sizes. The small run had 64 total initial individuals, and the large one had 512 initial individuals. We started a new generation after 32 individuals were evaluated, and both runs were given approximately the same 288 total compute hours, which roughly translates to around 24 hours of wall time. As you can see, the small run performed 109 generations, whereas the large run only performed 28 generations. The large run evaluated many more individuals, however, with evaluating 34,989 individuals as compared to 13,896 individuals on the small run. The best individual accuracy was roughly the same for both, however, and as you can see, the resulting Pareto fronts are also nearly identical. If we dive deeper into results, we see that both runs have the same general accuracy and accuracy over generation profiles. Moreover, the best accuracy observed in an individual improved over the course of the evolution, but it primarily improved during the early generations. We can conclude that EMADE does not take advantage of the larger population to optimize more quickly, and we believe this may be potentially due to the effects of seeding. On the right, you can see an example individual that was evolved. It applies the ski median filter data preprocessing primitive, and its neural network architecture consists of a VGG input layer followed by a single output layer, trained with the Agarwal optimizer with the batch size of 7. As you can see, it takes advantage of both EMADE preprocessing primitives as well as neural network-based primitives. It achieves a 71.1% test accuracy with around 14 million parameters. This individual shows that EMADE can evolve algorithms that take advantage of both data preprocessing primitives and neural network architectures. In this work, we show a proof of concept that uses neural evolution to look through research space to find optimal neural network architectures across different objectives for image classification tasks. We also show that EMADE can evolve algorithms that take advantage of both data preprocessing primitives and neural network architectures. So what are the next steps? We would like to test our results against other state-of-the-art algorithms and further investigate the benefits of manipulating the input data as part of the algorithmic search space. We'll be including more rigorous testing on other datasets, especially unbalanced ones, as well as drawing explicit comparisons to other AutoML frameworks. There are also multiple potential areas for improvements. We could do more architectural changes, such as supporting skip connections within nodes for trees, or expanding from tree-based neural networks to the more general graph-based neural networks. We could also work on developing ways to more efficiently evaluate individuals. However, the most interesting area of improvement is investigating building and preserving tree complexity, which might be possible with more preprocessing. We found that our hypothesis is that pre-trained models are doing so well that it's hard for evolution to build off of them. However, pre-trained models are certainly not going anywhere and will only get more relevant in the machine learning community, so we should find ways for pre-trained models and evolutionary computing to work together. As you can see our references, and are there any questions?